Yeah, here's your brain teaser. Get your paper shapes out alongside your notes. Take the shapes out of the bag. And find the DNA. Get all the shapes out and then find the DNA. There are many nucleotides that you've cut out so far. Those are all called nucleotides, but only some of them are DNA. Find the DNA.
Like all the DNA or just
one? Just one piece of DNA so that you can hold it up and show me that you know the difference. If you're kind of at a loss right now, look up on the screen and then just listen. You got it? You see the difference? What do you think the other thing you have in the bag that's not DNA is?
RNA.
Good. So what you have is basically half DNA, half RNA. Take a piece of DNA right now, hold it up for me so that I know that you know the difference.
I'll come back.
Again, if you need a hint, look up on the board. It might help you actually read the words on the paper shape. Most of you got it. You got it. You got it. I got it. Benny? You think you got it? Benny got it. Please. Yeah. So, in a nutshell here, Nathan, what's the difference? How did you know?
This one has the deoxyribose.
Easiest way to tell. They're the ones that say deoxyribose on them. And that is because DNA actually stands for, anyone? Oh, this is one you should write down. Oh, no. Slow. All right. Deoxyribonucleic acid. Acid. Yeah. Deoxyribonucleic acid. You should write that down. So you know some things already. What the parts are: deoxyribose, phosphate, those 4 nitrogenous bases: adenine, guanine, cytosine, and thymine. Remember, we left off in genetics with T.H. Morgan, the fruit fly guy. You remember him? Who had mapped genes to chromosomes. He figured out that genes are just places on chromosomes. Well, that guy, even knowing that, we still didn't know what the genetic material actually was. He didn't know it was DNA that was doing all the tricks. Because chromosomes are made of DNA and protein, and we weren't sure which one was the actual genetic material. So forward from like the 1920s and 30s to the 1950s, and we get to these guys. James Watson and Francis Crick. two scientists who would eventually win the Nobel Prize. With some major help from a female scientist who they then basically robbed of all the credit. Her name was Rosalind Franklin. Watson and Crick are basically at the point where you are right now. Someone has proved before them that DNA is the stuff. That DNA is the exciting part. DNA is the code. And we know the basic chemicals it's made of. We know about the deoxyribosome phosphate and the nitrogenous bases. What we don't know is how it all goes together. So right now, that's you. You get to play Watson and Crick right now. Take your DNA paper shapes, put the RNA back. Put the RNA back in the bag. Just have your DNA out there.
That's one or all of it. Next time we do a whole period. To do something like that. Do that. Put that inside. With the finger. Just one DNA? Or
Nope, all the DNA.
Okay.
What do you mean he didn't cut out his paper shapes? Well, the assignment was to cut out paper shapes, and he just didn't. It's going to sound silly. Just saying. Okay, so now you get to play Watson and Crick, where you see if you can figure out how all this goes together. It's a puzzle. The only rule in manipulating your paper shapes is this: you are not allowed to flip it over to the blank side. Move around, rotate all you want. You have to be able to see the writing. It doesn't have to be oriented so you can read it, but you can't, in other words, you can't put the ink facing the table.
Do they all fit together in one little thing?
I mean, kind of. Again, think of it as a puzzle. So, yes, the tab and slot thing is definitely functional, right? You can get them to fit together like that. But what about those other shapes? See if you can get more of an interlocking pattern. Some of you have gotten it real quick. Figured out the trick. One thing I will say is that if you're trying to make this work where you're fitting this angle, look up here, trying to fit that angle into this slot, right? That is not a puzzle piece that fits, right? That's not going to work. There's another thing that fits into this much better, a narrower angle. I'm getting it now. Yeah, you're getting the trick. So what, I mean, it's not really even much of a trick, but Hazen, what is the thing that you sort of have to do to get these to work?
Put them together.
Nathan, you figured it out. If someone were confused, what would you tell them?
Put the tabs in and then either the circle or the triangle in each other.
You notice that the circles and the triangles kind of match. And to get it to work, what do you have to do with one strand as opposed to the other strand, Riley? Yeah, so if you do the tab slot thing and make one strand of DNA, to get the other strand to kind of mate up with it, you got to flip it upside down, right? It has to be so that the words are upside down. Looks like most of you have gotten that, no problem, just right. Yeah, so that's actually what Watson and Crick had to do. They had to basically figure out that the stuff was upside down. It was two strands, and that they were kind of winding around each other in what they ended up calling a double helix. Sort of a twisted ladder shape, as you can see in my model up here, right? That's the 3D version. If you were to take yours and tape it together and put it vertically and kind of twist it, that's the basic idea of the double helix. And the word they used for the upside down part, where you got to have the strands running opposite directions to get them to mate up, the word they use is anti-parallel, right? They're parallel, but in opposite directions. So the parts in the middle of, if you consider this a ladder, what they then figure out, building on somebody else's work for this as well, is that the middle part of the ladder is all nitrogenous bases. That's what we call those adenine, guanine, cytosine, thymine. They're all nitrogenous bases in the middle. Most of this chemical is held together with what we call covalent bonds, which are electron sharing bonds. In the middle, though, different kind of bond. It's called a weak hydrogen bond. Much easier bond to break, which is where the reading and transmitting of the DNA code happens, when these weak hydrogen bonds get broken in different ways. And they figure out by actually someone else measuring the amount of adenine, thymine, guanine, and cytosine in DNA, they figure out that it's always adenine bonding with thymine, and it's always cytosine bonding with guanine. That is something you are absolutely going to have to remember again and again and again this chapter. Which ones pair up with which ones? So since you're going to have to memorize that, and you know me, I'm all about stupid ways to remember stuff. Here is literally how I remember this almost every time I have to remember it. Adenine pairs with thymine, adenine pairs with thymine, guanine pairs with cytosine. How I remember it is those capital letters. These two are both made of straight lines, so they go together, right? A, T. Whereas these two have curvy lines. The G and the C go together because they both have curvy lines. That is the kindergarten way I remember base pairing, which is what we call it. In fact, we call it complementary base pairing. By the way, they were stuck on this. They had not figured it out. They were at a dead end as far as how this thing arranges itself, because they couldn't figure out the whole twisty part. Because that's how it actually is in real life. Yeah. Right? You can't understand it if it's just flat. To figure out the twisty part, which is really how it all goes together, they actually had their buddy Maurice, all I remember is his first name was Maurice Wilkins, who worked in the same lab as this lady, Rosalind Franklin, who was a brilliant molecular photographer. She used a new technique called X-ray crystallography. And he basically took, without her consent, this picture, which is kind of looking down the barrel of a DNA molecule like this. And it was all they needed. It was like, oh, I see. The thingies go in the middle, and the thingies twist around on the outside, and that's it. So that's how they figured it out. Again, we call this complementary base pairing. there's an almost endless variety of cartoons and drawings and stuff to help you remember which ones pair with which. Complementary, by the way, don't spell it wrong. Complementary with an E as opposed to an I in this spot right here. Do you understand the difference? Like if I say, Caleb, that's a really nice sweatshirt.
Oh, thank you.
That's me being complimentary with an I, right? I'm paying you a compliment. But if I say, Caleb, that sweatshirt goes with your eyes very nicely, picks up the color. They are complementary, your sweatshirt and your eyes. That's complementary with an E. It means they go together. Warm fuzzies all day. Unless you didn't cut out James. Questions? Okay, keep that DNA out of the bag. I have an activity for you. DNA and RNA paper shaped lab is what it says at the top. Try not to move too much air in here.
Okay.
So this worksheet will start to take you through some of the chemical stuff about DNA, and then it'll have you moving pieces around and fitting them together and so on. Follow directions. I'll try and explain a couple of the things that might be slightly confusing. Starting with number one. Number one says, what is the molecular formula of deoxyribose? Do you know what a molecular formula is? You do. You haven't thought of it that way, maybe, but it's like literally the molecular formula of water is H2O. It's how many of each atom the molecule has, right? So they actually give you the three elements that deoxyribose is made of, which is C, H, and O. Your job is to put a number in each of those three spots when you count how many of each atom there is. And you have to look over to the box on the right. Okay, that upper left molecule is deoxyribose. Okay, so you just have to count the C's, H's, and O's and put the numbers in those spots. That's how you answer that question. Make sense? Okay, I'm gonna let you work. You need to get through part A today.